Hello, welcome to Advanced Composites. Today is the last day of the second week of this particular course. Yesterday, we just developed a relation between stresses and strains in a especially orthotropic material loaded in a plane stress condition in a situation in a general reference frame. So, there we were not specifically aligned to a particular material axis system. We were just making sure that the material is orthotropic and it is thin, and because it is thin it will have a plane stress condition, and for that condition the relationship between stresses and strains in a general xy coordinate system we had expressed was this: sigma with respect to xy coordinate system equals q bar matrix times the strain vector with respect to xy coordinate system. And to recap, q bar matrix is nothing but inverse of transformation matrix T1 times q matrix times transformation matrix T2. So, we know what exactly T1 matrix is. So, we can take its inverse, we know what is T2 matrix, and if we do all the computation, the relationship between q bars and q's come out like this. So, q11 bar equals qv11 times cosine 4 theta. So, C means cosine, okay, and S means sin theta. So, q11 is equal to q11 bar times cosine 4 theta plus q22 sin 4 theta plus 2 q12 plus 2 q66 times sin square theta cosine square theta. Similarly, q22 bar is equal to q11 sin 4 theta plus q22 cosine 4 theta plus 2 times this entire expression times sin square theta cosine square theta, and q12 bar equals sin square theta. So, q12 bar is equal to q11 plus q22 minus 4 q66 times sin square theta cosine square theta plus q12 cosine 4 theta plus sin 4 theta. Now, the Q matrix was having q16 and q26 as 0, but in the q bar matrix q16 bar is not 0. So, I will write down the expression for that. So, that equals q11 minus q12 minus 2 q66 cosine cube theta sin minus q22 minus q12 minus 2 q66 cosine theta sin cube theta, and q26 bar equals the same thing, but it is cosine theta sin cube theta minus same terms in this bracket, and this is cosine cube theta sin theta. And finally, the expression for q66 bar. So, that equals q11 plus q22 minus twice q12 minus twice Q66 sine square cosine square plus Q66 times sine 4 theta plus cosine 4 theta. Okay. And we will spend a couple of minutes looking at these expressions and I will make some observations. Q11 and Q22 and also Q12, their values do not change if I change the value of theta from plus theta to minus theta. How are they dependent on theta? They are dependent on cosine 4 theta. So, if I change from cosine 4 theta to cosine 4 of minus theta, it is the same value. Sine 4 theta, sine square theta, cosine square theta. The same is also true for Q66. It is also true for Q66. Its value also does not change if I switch my theta to minus theta. So, if theta is 30 degrees and in the other case if it is minus 30 degrees, the values of Q11 bar, Q22 bar, Q12 bar and Q66 bar, they do not change, they remain same. But, so these are even functions of theta. So, these are even in theta, this is also even in theta. But Q16 bar and Q26 bar, let us look at these. So, when I change from theta degrees to minus theta degrees, cosine cube does not change because cosine of positive theta and negative theta is the same, but sine theta changes, the sine theta changes to negative sine theta. Similarly, the sine cube theta also changes. So, for this reason Q16 bar and Q26 bar are odd functions in theta. The other thing I would like to say is that because Q16 bar and Q26 bar, they are not necessarily 0, this mathematically implies that extensional strains or extensional stresses, they can generate shear strains. And shear stresses, they can generate extensional strains and vice versa. This was not the case for especially orthotropic material because Q16 and Q26 were 0. But once we move to the land of general orthotropy, then there is a coupling between shear and extensional effects. Okay. So, if you have a rectangular sample and you pull it, it will not only become longer, but it will also deform and its angles at the corners will change from 90 degrees to something different. And it is important to note that the direction of this coupling is sensitive to theta. So, if you change from positive theta to negative theta, its direction reverses, because Q16 and Q26 bar are odd functions of theta. So, it is important to get our conventions right. So, whenever we measure theta, this is the convention we follow, otherwise we will not get our shear strains and things like that, or we will not get our solutions correct, okay, because of the sensitivity of Q16 bar and Q26 bar to the direction of theta. So, we should be clear on our conventions which are consistent with the conventions we have used in this formulation. So, I can once again write my stress vector in xy coordinate system as q bar matrix times strain vector. If I multiply both sides of this equation by inverse of q bar matrix, then I can express strain in terms of in terms of a compliance matrix and stress. So, this gives me strain vector is equal to S bar matrix times stress vector. Okay. So, S bar is compliance matrix and it is nothing but inverse of q bar. So, the mathematical relations between different q bars and S bars is this. So, this is equal to S11 C4 plus S22 S4 plus 2 S12 plus S66 S square C square. S22 bar equals S11 S4 plus S22 C4 plus 2, this entire thing S square C square, and S12 bar equals S11 plus S22 S66 S square C square plus S12 times C4 plus S4, and then S66 is equal to twice of S11 plus 2 of S22 minus 4 of S12 minus S66 cosine square sine square plus S66 cosine 4 plus sine 4. S16 bar equals 2 S11 minus 2 S12 minus S66 cosine cube theta sine minus 2 S22 minus 2 S12. So, there is a small error here, this is 2 in bracket. Okay. So, it is 2 minus S66 cosine sine cube, and S26 bar equals the same thing times sine cube cosine minus this thing sine cosine cube. So, once again we see that S11 bar, S22 bar, S12 bar and S66 bar, they are all even in theta, while these two guys S16 bar and S26 bar, they are all odd in theta. So, it is important to understand that. Lastly, I will write stress strain relationships between stress and strain relationships in terms of engineering constants. So, those relationships are given here, epsilon x, epsilon y, gamma x y equals 1 over E x minus nu x y over E y minus m x over E L minus nu x y over E x 1 over E y and minus m y over E L, and this is minus m x over E L minus m y over E L and 1 over g x y times sigma x, sigma y, tau x y. So, these are the stress strain relationship for a generally orthotropic material which is in a state of plane stress in terms of engineering constants, engineering stiffness constants of the material, which are E x, E y, E L, m x, m y and so on and so forth. So, here m x and m y, if these terms were 0, then there will not be any shear extensional coupling. So, these are the cross coefficients, these are called cross coefficients. And what do? They once again they couple the extensional response to the shear response and vice versa. The relationships for E x, E y, nu x y, g x y, m x, m y. So, these 6 we have already explained these relationships in our previous course. So, you please go back and refer to that and you will find the relation. So, that E x, E y, nu x y, g x y, m x, m y, all of these things can be calculated in terms of E L, E t, G L t, nu L t and the transformation angle theta. So, even though these are 6 constants, but they can be expressed in terms of these 4 fundamentally independent constants for this orthotropic material under plane stress state. So, that concludes our discussion for today and also the content which I wanted to cover in this week. I hope you have a wonderful weekend. If you have any questions, please do send us emails, and next week we will move on to another topic where we will start discussing the behavior of laminates in terms of these constants and how we can relate stresses and strains in case of laminates. So, with that I conclude our discussion. Have a great day and a wonderful weekend. Thank you.